1910.1027 Appendix E, Cadmium in Workplace Atmospheres. Method Number, ID 189. Matrix, Air. OSHA Permissible Exposure Limits, 5 micrograms per cubic meter, TWA, 2.5 micrograms per cubic meter, Action Level TWA. Collection Procedure: a known volume of air is drawn through a 37 mm diameter filter cassette containing a 0.8 m mixed cellulose ester membrane filter, MCEF. Recommended air volume, 960 L. Recommended sampling rate, 2.0 liters per minute. Analytical procedure: air filter samples are digested with nitric acid. After digestion, a small amount of hydrochloric acid is added. The samples are then diluted to volume with deionized water and analyzed by either flame atomic absorption spectroscopy, AS, or flameless atomic absorption spectroscopy using a heated graphite furnace atomizer, ASHGA. Detection limits: qualitative, 0.2 micrograms per cubic meter for a 200 L sample by flame AS, 0.007 micrograms per cubic meter for a 60 L sample by ASHGA. Quantitative, 0.70 micrograms per cubic meter for a 200 L sample by flame AS, 0.025 micrograms per cubic meter for a 60 L sample by ASHGA. Precision and accuracy: flame AAS analysis and AASHGA analysis. Validation level: 2.5 to 10 micrograms per cubic meter for a 400 L air vol, 1.25 to 5.0 micrograms per cubic meter for a 60 L air vol. CV1, pooled 0.010, 0.043. Analytical bias, plus 4%, minus 5.8%. Overall analytical error at plus or minus 6.0%, plus or minus 14.2%. Method classification, validated. Date, June, 1992. Inorganic Service Branch 2, OSHA Salt Lake Technical Center, Salt Lake City, Utah. Commercial manufacturers and products mentioned in this method are for descriptive use only and do not constitute endorsements by OSHA. Similar products from other sources can be substituted. 1. Introduction. 1.1. Scope. This method describes the collection of airborne elemental cadmium and cadmium compounds on 0.8 m mixed cellulose ester membrane filters and their subsequent analysis by either flame atomic absorption spectroscopy, AS, or flameless atomic absorption spectroscopy using a heated graphite furnace atomizer, ASHGA. It is applicable for both TWA and action level TWA permissible exposure level, PL, measurements. The two atomic absorption analytical techniques included in the method do not differentiate between cadmium fume and cadmium dust samples. They also do not differentiate between elemental cadmium and its compounds. 1.2. Principle. Airborne elemental cadmium and cadmium compounds are collected on a 0.8 m mixed cellulose ester membrane filter, MCEF. The air filter samples are digested with concentrated nitric acid to destroy the organic matrix and dissolve the cadmium analytes. After digestion, a small amount of concentrated hydrochloric acid is added to help dissolve other metals which may be present. The samples are diluted to volume with deionized water and then aspirated into the oxidizing air/acetylene flame of an atomic absorption spectrophotometer for analysis of elemental cadmium. If the concentration of cadmium in a sample solution is too low for quantitation by this flame AAS analytical technique, and the sample is to be averaged with other samples for TWA calculations, aliquots of the sample and a matrix modifier are later injected onto a LVOF platform in a pyrolytically coated graphite tube of a Zeeman atomic absorption spectrophotometer/graphite furnace assembly for analysis of elemental cadmium. The matrix modifier is added to stabilize the cadmium metal and minimize sodium chloride as an interference during the high temperature charring step of the analysis. 5.1, 5.2. 1.3. History. Previously, two OSHA sampling and analytical methods for cadmium were used concurrently, 5.3, 5.4. Both of these methods also required 0.8 m mixed cellulose ester membrane filters for the collection of air samples. These cadmium air filter samples were analyzed by either flame atomic absorption spectroscopy, 5.3, or inductively coupled plasma/atomic emission spectroscopy, ICPAS, 5.4. Neither of these two analytical methods have adequate sensitivity for measuring workplace exposure to airborne cadmium at the new lower TWA and action level TWA-PL levels when consecutive samples are taken on one employee and the sample results need to be averaged with other samples to determine a single TWA. The inclusion of two atomic absorption analytical techniques in the new sampling and analysis method for airborne cadmium permits quantitation of sample results over a broad range of exposure levels and sampling periods. The flame AAS analytical technique included in this method is similar to the previous procedure given in the General Metals Method ID 121, 5.3, with some modifications. The sensitivity of the AAS-HGA analytical technique included in this method is adequate to measure exposure levels at 1/10 the action level TWA, or lower, when less than full shift samples need to be averaged together. 1.4. Properties, 5.5. Elemental cadmium is a silver-white, blue-tinged, lustrous metal which is easily cut with a knife. It is slowly oxidized by moist air to form cadmium oxide. It is insoluble in water, but reacts readily with dilute nitric acid. Some of the physical properties and other descriptive information of elemental cadmium are given below. CAS number 7440-43-9, atomic number 48, atomic symbol CD, atomic weight 112.41, melting point 321 degrees Celsius, boiling point 765 degrees Celsius. Density 8.65 g/ml, 25 degrees Celsius. The properties of specific cadmium compounds are described in reference 5.5. 1.5. Method performance. A synopsis of method performance is presented below. Further information can be found in section 4. 1.5.1. The qualitative and quantitative detection limits for the flame AAS analytical technique are 0.04 g, 0.004 g/ml, and 0.14 g, 0.014 g/ml cadmium, respectively, for a 10 ml solution volume. These correspond, respectively, to 0.2 micrograms per cubic meter and 0.70 micrograms per cubic meter for a 200 L air volume. 1.5.2. The qualitative and quantitative detection limits for the AAS-HGA analytical technique are 0.44 Ing, 0.044 nanograms per milliliter, and 1.5 Ing, 0.15 nanograms per milliliter, cadmium, respectively, for a 10 ml solution volume. These correspond, respectively, to 0.007 micrograms per cubic meter and 0.025 micrograms per cubic meter for a 60 L air volume. 1.5.3. The average recovery by the flame AAS analytical technique of 17 spiked MCF samples containing cadmium in the range of 0.5 to 2.0 times the TWA target concentration of 5 micrograms per cubic meter, assuming a 400 L air volume, was 104% with a pooled coefficient of variation, CV1, of 0.010. The flame analytical technique exhibited a positive bias of +4% for the validated concentration range. The overall analytical error, OAE, for the flame AAS analytical technique was plus or minus 6.0%. 1.5.4. The average recovery by the AAS-HGA analytical technique of 18 spiked MCF samples containing cadmium in the range of 0.5 to 2.0 times the action level TWA target concentration of 2.5 micrograms per cubic meter, assuming a 60 L air volume, was 94.2% with a pooled coefficient of variation, CV1, of 0.043. The AAS-HGA analytical technique exhibited a negative bias of minus 5.8% for the validated concentration range. The overall analytical error, OAE, for the AAS-HGA analytical technique was plus or minus 14.2%. 1.5.5. Sensitivity in flame atomic absorption is defined as the characteristic concentration of an element required to produce a signal of 1% absorbance, 0.0044 absorbance units. Sensitivity values are listed for each element by the atomic absorption spectrophotometer manufacturer and have proved to be a very valuable diagnostic tool to determine if instrumental parameters are optimized and if the instrument is performing up to specification. The sensitivity of the spectrophotometer used in the validation of the flame AAS analytical technique agreed with the manufacturer's specifications. 5.6. The 2G/ml cadmium standard gave an absorbance reading of 0.350 abs. Units. 1.5.6. Sensitivity in graphite furnace atomic absorption is defined in terms of the characteristic mass, the number of picograms required to give an integrated absorbance value of 0.0044 absorbance second. 5.7. Data suggests that under stabilized temperature platform furnace (STPF) conditions, see section 1.6.2, characteristic mass values are transferable between properly functioning instruments to an accuracy of about 20%, 5.2. The characteristic mass for STPF analysis of cadmium with Zeeman background correction listed by the manufacturer of the instrument used in the validation of the AASHGA analytical technique was 0.35 pg. The experimental characteristic mass value observed during the determination of the working range and detection limits of the AASHGA analytical technique was 0.41 pg. 1.6. Interferences. 1.6.1. High concentrations of silicate interfere in determining cadmium by flame AAS. 5.6. However, silicates are not significantly soluble in the acid matrix used to prepare the samples. 1.6.2. Interferences, such as background absorption, are reduced to a minimum in the AASHGA analytical technique by taking full advantage of the stabilized temperature platform furnace (STPF) concept. STPF includes all of the following parameters: 5.2. A. Integrated absorbance. B. Fast instrument electronics and sampling frequency. C. Background correction. D. Maximum power heating. E. Atomization off the LVOF platform in a pyrolytically coated graphite tube. F. Gas stop during atomization. G. Use of matrix modifiers. 1.7. Toxicology. 5.14. Information listed within this section is synopsis of current knowledge of the physiological effects of cadmium and is not intended to be used as the basis for OSHA policy. IARC classifies cadmium and certain of its compounds as Group 2A carcinogens, probably carcinogenic to humans. Cadmium fume is intensely irritating to the respiratory tract. Workplace exposure to cadmium can cause both chronic and acute effects. Acute effects include tracheobronchitis, pneumonitis, and pulmonary edema. Chronic effects include anemia, rhinitis/anosmia, pulmonary emphysema, proteinuria, and lung cancer. The primary target organs for chronic disease are the kidneys, non-carcinogenic, and the lungs, carcinogenic. 2. Sampling. 2.1. Apparatus. 2.1.1. Filter cassette unit for air sampling. A 37 mm diameter mixed cellulose ester membrane filter with a pore size of 0.8 m contained in a 37 mm polystyrene 2 or 3-piece cassette filter holder. Part No. MAWP 037A0, Millipore Corporation, Bedford, Massachusetts. The filter is supported with a cellulose backup pad. The cassette is sealed prior to use with a shrinkable gel band. 2.1.2. A calibrated personal sampling pump whose flow is determined to an accuracy of plus or minus 5% at the recommended flow rate with the filter cassette unit in line. 2.2. Procedure. 2.2.1. Attach the prepared cassette to the calibrated sampling pump. The backup pad should face the pump, using flexible tubing. Place the sampling device on the employee such that air is sampled from the breathing zone. 2.2.2. Collect air samples at a flow rate of 2.0 liters per minute. If the filter does not become overloaded, a full shift, at least 7 hours, sample is strongly recommended for TWA and action level TWA measurements with a maximum air volume of 960 L. If overloading occurs, collect consecutive air samples for shorter sampling periods to cover the full work shift. 2.2.3. Replace the end plugs into the filter cassettes immediately after sampling. Record the sampling conditions. 2.2.4. Securely wrap each sample filter cassette end-to-end with an OSHA Form 21 sample seal. 2.2.5. Submit at least one blank sample with each set of air samples. The blank sample should be handled the same as the other samples except that no air is drawn through it. 2.2.6. Ship the samples to the laboratory for analysis as soon as possible in a suitable container designed to prevent damage in transit. 3. Analysis. 3.1. Safety precautions. 3.1.1. Wear safety glasses, protective clothing, and gloves at all times. 3.1.2. Handle acid solutions with care. Handle all cadmium samples and solutions with extra care. See SECT. 1.7. Avoid their direct contact with work area surfaces, eyes, skin, and clothes. Flush acid solutions which contact the skin or eyes with copious amounts of water. 3.1.3. Perform all acid digestions and acid dilutions in an exhaust hood while wearing a face shield. To avoid exposure to acid vapors, do not remove beakers containing concentrated acid solutions from the exhaust hood until they have returned to room temperature and have been diluted or emptied. 3.1.4. Exercise care when using laboratory glassware. Do not use chipped pipettes, volumetric flasks, beakers, or any glassware with sharp edges exposed in order to avoid the possibility of cuts or abrasions. 3.1.5. Never pipette by mouth. 3.1.6. Refer to the instrument instruction manuals and SOPs, 5.8, 5.9, for proper and safe operation of the atomic absorption spectrophotometer, graphite furnace atomizer, and associated equipment. 3.1.7. Because metallic elements and other toxic substances are vaporized during AAS flame or graphite furnace atomizer operation, it is imperative that an exhaust vent be used. Always ensure that the exhaust system is operating properly during instrument use. 3.2. Apparatus for sample and standard preparation. 3.2.1. Hot plate, capable of reaching 150 degrees Celsius, installed in an exhaust hood. 3.2.2. Phillips beakers, 125 milliliters. 3.2.3. Bottles, narrowmouth, polyethylene or glass with leak-proof caps, used for storage of standards and matrix modifier. 3.2.4. Volumetric flasks, volumetric pipettes, beakers, and other associated general laboratory glassware. 3.2.5. Forceps and other associated general laboratory equipment. 3.3. Apparatus for flame AAS analysis. 3.3.1. Atomic absorption spectrophotometer consisting of an nebulizer and burner head, pressure regulating devices capable of maintaining constant oxidant and fuel pressures, optical system capable of isolating the desired wavelength of radiation, 228.8 nanometers, adjustable slit, light measuring and amplifying device, display, strip chart, or computer interface for indicating the amount of absorbed radiation, cadmium hollow cathode lamp or electrodeless discharge lamp, EDL, and power supply. 3.3.2. Oxidant, compressed air, filtered to remove water, oil, and other foreign substances. 3.3.3. Fuel, standard commercially available tanks of acetylene dissolved in acetone. Tanks should be equipped with flash arresters. Caution: do not use grades of acetylene containing solvents other than acetone because they may damage the PVC tubing used in some instruments. 3.3.4. Pressure reducing valves, 2-gauge, 2-stage pressure regulators to maintain fuel and oxidant pressures somewhat higher than the controlled operating pressures of the instrument. 3.3.5. Exhaust vent installed directly above the spectrophotometer burner head. 3.4. Apparatus for AAS-HGA analysis. 3.4.1. Atomic absorption spectrophotometer consisting of an heated graphite furnace atomizer, HGA, with argon purge system, pressure regulating devices capable of maintaining constant argon purge pressure, optical system capable of isolating the desired wavelength of radiation, 228.8 nanometers, adjustable slit, light measuring and amplifying device, display, strip chart, or computer interface for indicating the amount of absorbed radiation as integrated absorbance, peak area, background corrector, xenon or deuterium arc. The xenon background corrector is recommended. Cadmium hollow cathode lamp or electrodeless discharge lamp, EDL, and power supply. Autosampler capable of accurately injecting 5 to 20 L sample aliquots onto the LOF platform in a graphite tube. 3.4.2. Pyrolytically coated graphite tubes containing solid, pyrolytic LOF platforms. 3.4.3. Polyethylene sample cups, 2.0 to 2.5 milliliters, for use with the autosampler. 3.4.4. Inert purge gas for graphite furnace atomizer, compressed gas cylinder of purified argon. 3.4.5. 2-gauge, 2-stage pressure regulator for the argon gas cylinder. 3.4.6. Cooling water supply for graphite furnace atomizer. 3.4.7. Exhaust vent installed directly above the graphite furnace atomizer. 3.5. Reagents. All reagents should be ACS analytical reagent grade or better. 3.5.1 Deionized water with a specific conductance of less than 10s. 3.5.2 Concentrated nitric acid, HNO3. 3.5.3 Concentrated hydrochloric acid, HCl. 3.5.4 Ammonium phosphate, monobasic, NH4H2PO4. 3.5.5 Magnesium nitrate, Mg, NO3, 26H2O. 3.5.6 Diluting solution, 4% HNO3, 0.4% HCl at 40 ml HNO3 and 4 ml HCl carefully to approximately 500 ml deionized water and dilute to 1L with deionized water. 3.5.7 Cadmium standard stock solution, 1000 g/ml. Use a commercially available certified 1000 g/ml cadmium standard or, alternatively, dissolve 1.0000 g of cadmium metal in a minimum volume of 1:1 HCl and dilute to 1L with 4% HNO3. Observe expiration dates of commercial standards. Properly dispose of commercial standards with no expiration dates or prepared standards 1 year after their receipt or preparation date. 3.5.8 Matrix modifier for ASHGA analysis. Dissolve 1.0 g NH4H2PO4 and 0.15 g Mg, NO3, 26H2O in approximately 200 ml deionized water. Add 1 ml HNO3 and dilute to 500 ml with deionized water. 3.5.9 Nitric acid, 1:1 HNO3/DiH2O mixture. Carefully add a measured volume of concentrated HNO3 to an equal volume of DiH2O. March 5, 10. Nitric acid, 10% V/V. Carefully add 100 ml of concentrated HNO3 to 500 ml of DiH2O and dilute to 1L. 3.6 Glassware preparation. 3.6.1 Clean Phillips beakers by refluxing with 1:1 nitric acid on a hot plate in a fume hood. Thoroughly rinse with deionized water and invert the beakers to allow them to drain dry. 3.6.2 Rinse volumetric flasks and all other glassware with 10% nitric acid and deionized water prior to use. 3.7 Standard preparation for flame AAS analysis. 3.7.1 Dilute stock solutions. Prepare 1, 5, 10 and 100 g/ml cadmium standard stock solutions by making appropriate serial dilutions of 1000 g/ml cadmium standard stock solution with the diluting solution described in section 3.5.6. 3.7.2 Working standards. Prepare cadmium working standards in the range of 0.02 to 2.0 g/ml by making appropriate serial dilutions of the dilute stock solutions with the same diluting solution. A suggested method of preparation of the working standards is given below. Store the working standards in 500 ml narrowmouth polyethylene or glass bottles with leak-proof caps. Prepare every 12 months. 3.8 Standard preparation for AASHGA analysis. 3.8.1 Dilute stock solutions. Prepare 10, 100 and 1000 nanograms per milliliter cadmium standard stock solutions by making appropriate tenfold serial dilutions of the 1000 g/ml cadmium standard stock solution with the diluting solution described in section 3.5.6. 3.8.2 Working standards. Prepare cadmium working standards in the range of 0.2 to 20 nanograms per milliliter by making appropriate serial dilutions of the dilute stock solutions with the same diluting solution. A suggested method of preparation of the working standards is given below. Store the working standards in narrowmouth polyethylene or glass bottles with leak-proof caps. Prepare monthly. 3.9 Sample preparation. 3.9.1 Carefully transfer each sample filter with forceps from its filter cassette unit to a clean, separate 125 ml Phillips beaker along with any loose dust found in the cassette. Label each Phillips beaker with the appropriate sample number. 3.9.2 Digest the sample by adding 5 ml of concentrated nitric acid, HNO3, to each Phillips beaker containing an air filter sample. Place the Phillips beakers on a hot plate in an exhaust hood and heat the samples until approximately 0.5 ml remains. The sample solution in each Phillips beaker should become clear. If it is not clear, digest the sample with another portion of concentrated nitric acid. 3.9.3. After completing the HNO3 digestion and cooling the samples, add 40 L, 2 drops, of concentrated HCl to each air sample solution and then swirl the contents. Carefully add about 5 milliliters of deionized water by pouring it down the inside of each beaker. 3.9.4. Quantitatively transfer each cooled air sample solution from each Phillips beaker to a clean 10 milliliters volumetric flask. Dilute each flask to volume with deionized water and mix well. 3.10. Flame AAS analysis. Analyze all of the air samples for their cadmium content by flame atomic absorption spectroscopy, AAS, according to the instructions given below. 3.10.1. Set up the atomic absorption spectrophotometer for the air/acetylene flame analysis of cadmium according to the SOP 5.8, or the manufacturer's operational instructions. For the source lamp, use the cadmium hollow cathode or electrodeless discharge lamp operated at the manufacturer's recommended rating for continuous operation. Allow the lamp to warm up 10 to 20 minutes or until the energy output stabilizes. Optimize conditions such as lamp position, burner head alignment, fuel and oxidant flow rates, etc. See the SOP or specific instrument manuals for details. Instrumental parameters for the Perkin-Elmer Model 603 used in the validation of this method are given in Attachment 1. 3.10.2. Aspirate and measure the absorbance of a standard solution of cadmium. The standard concentration should be within the linear range. For the instrumentation used in the validation of this method, a 2G/ml cadmium standard gives a net absorbance reading of about 0.350 abs. Units, see section 1.5.5, when the instrument and the source lamp are performing to manufacturer specifications. 3.10.3. To increase instrument response, scale expand the absorbance reading of the aspirated 2G/ml working standard approximately 4 times. Increase the integration time to at least 3 seconds to reduce signal noise. 3.10.4. Auto-zero the instrument while aspirating a deionized water blank. Monitor the variation in the baseline absorbance reading, baseline noise, for a few minutes to ensure that the instrument, source lamp and associated equipment are in good operating condition. 3.10.5. Aspirate the working standards and samples directly into the flame and record their absorbance readings. Aspirate the deionized water blank immediately after every standard or sample to correct for and monitor any baseline drift and noise. Record the baseline absorbance reading of each deionized water blank. Label each standard and sample reading and its accompanying baseline reading. 3.10.6. It is recommended that the entire series of working standards be analyzed at the beginning and end of the analysis of a set of samples to establish a concentration response curve. Ensure that the standard readings agree with each other and are reproducible. Also, analyze a working standard after every 5 or 6 samples to monitor the performance of the spectrophotometer. Standard readings should agree within plus or minus 10 to 15% of the readings obtained at the beginning of the analysis. 3.10.7. Bracket the sample readings with standards during the analysis. If the absorbance reading of a sample is above the absorbance reading of the highest working standard, dilute the sample with diluting solution and reanalyze. Use the appropriate dilution factor in the calculations. 3.10.8. Repeat the analysis of approximately 10% of the samples for a check of precision. 3.10.9. If possible, analyze quality control samples from an independent source as a check on analytical recovery and precision. March 10, 10. Record the final instrument settings at the end of the analysis. Date and label the output. 3.11. ASHGA analysis. Initially analyze all of the air samples for their cadmium content by flame atomic absorption spectroscopy, AAS, according to the instructions given in section 3.10. If the concentration of cadmium in a sample solution is less than 3 times the quantitative detection limit, 0.04 G/ml, 40 nanograms per milliliter, for the instrumentation used in the validation, and the sample results are to be averaged with other samples for TWA calculations, proceed with the ASHGA analysis of the sample as described below. 3.11.1. Set up the atomic absorption spectrophotometer and HGA for flameless atomic absorption analysis of cadmium according to the SOP 5.9 or the manufacturer's operational instructions and allow the instrument to stabilize. The graphite furnace atomizer is equipped with a pyrolytically coated graphite tube containing a pyrolytic platform. For the source lamp, use a cadmium hollow cathode or electrodeless discharge lamp operated at the manufacturer's recommended setting for graphite furnace operation. The Xenon background corrector and EDL are recommended for use with the LOF platform. Instrumental parameters for the Perkin-Elmer Model 5100 spectrophotometer and Xenon HGA 600 graphite furnace used in the validation of this method are given in attachment 2. 3.11.2. Optimize the energy reading of the spectrophotometer at 228.8 nanometers by adjusting the lamp position and the wavelength according to the manufacturer's instructions. 3.11.3. Set up the autosampler to inject a 5L aliquot of the working standard, sample or reagent blank solution onto the LOF platform along with a 10L overlay of the matrix modifier. 3.11.4. Analyze the reagent blank, diluting solution, section 3.5.6, and then auto-zero the instrument before starting the analysis of a set of samples. It is recommended that the reagent blank be analyzed several times during the analysis to assure the integrated absorbance, peak area, reading remains at or near zero. 3.11.5. Analyze a working standard approximately midway in the linear portion of the working standard range 2 or 3 times to check for reproducibility and sensitivity, see sections 1.5.5 and 1.5.6, before starting the analysis of samples. Calculate the experimental characteristic mass value from the average integrated absorbance reading and injection volume of the analyzed working standard. Compare this value to the manufacturer's suggested value as a check of proper instrument operation. 3.11.6. Analyze the reagent blank, working standard, and sample solutions. Record and label the peak area, ABS-SEC, readings and the peak and background peak profiles on the printer/plotter. 3.11.7. It is recommended the entire series of working standards be analyzed at the beginning and end of the analysis of a set of samples. Establish a concentration response curve and ensure standard readings agree with each other and are reproducible. Also, analyze a working standard after every 5 or 6 samples to monitor the performance of the system. Standard readings should agree within plus or minus 15% of the readings obtained at the beginning of the analysis. 3.11.8. Bracket the sample readings with standards during the analysis. If the peak area reading of a sample is above the peak area reading of the highest working standard, dilute the sample with the diluting solution and reanalyze. Use the appropriate dilution factor in the calculations. 3.11.9. Repeat the analysis of approximately 10% of the samples for a check of precision. March 11, 10. If possible, analyze quality control samples from an independent source as a check of analytical recovery and precision. March 11, 11. Record the final instrument settings at the end of the analysis. Date and label the output. 3.12. Calculations. Note, standards used for HGA analysis are in Ing/ml. Total amounts of cadmium from calculations will be in Ing, not G, unless a prior conversion is made. 3.12.1. Correct for baseline drift and noise in flame AAS analysis by subtracting each baseline absorbance reading from its corresponding working standard or sample absorbance reading to obtain the net absorbance reading for each standard and sample. 3.12.2. Use a least squares regression program to plot a concentration response curve of net absorbance reading, or peak area for HGA analysis, versus concentration, G/ml or Ing/ml, of cadmium in each working standard. 3.12.3. Determine the concentration, G/ml or Ing/ml, of cadmium in each sample from the resulting concentration response curve. If the concentration of cadmium in a sample solution is less than 3 times the quantitative detection limit, 0.04 G/ml, 40 nanograms per milliliter, for the instrumentation used in the validation of the method, and if consecutive samples were taken on one employee and the sample results are to be averaged with other samples to determine a single TWA, reanalyze the sample by AAS-HGA as described in section 3.11. And report the AAS-HGA analytical results. 3.12.4. Calculate the total amount, G or Ing, of cadmium in each sample from the sample solution volume, ml. W equals C, sample vol, ml, df, where W equals total cadmium in sample, C equals calculated concentration of cadmium, df equals dilution factor, if applicable. 3.12.5. Make a blank correction for each air sample by subtracting the total amount of cadmium in the corresponding blank sample from the total amount of cadmium in the sample. 3.12.6. Calculate the concentration of cadmium in an air sample, Mg/m3 or G/m3, by using one of the following equations. Mg/m3 equals WBc/air vol sampled, L, or G/m3 equals WBc 1000 Ing/G/air vol sampled, L, where WBc equals blank corrected total G cadmium in the sample. 1G equals 1000 Ing. 4. Backup data. 4.1. Introduction. 4.1.1. The purpose of this evaluation is to determine the analytical method recovery, working standard range, and qualitative and quantitative detection limits of the two atomic absorption analytical techniques included in this method. The evaluation consisted of the following experiments. 1. An analysis of 24 samples, 6 samples each at 0.1, 0.5, 1 and 2 times the TWAPL, for the analytical method recovery study of the flame AAS analytical technique. 2. An analysis of 18 samples, 6 samples each at 0.5, 1 and 2 times the action level TWAPL, for the analytical method recovery study of the AAS-HGA analytical technique. 3. Multiple analyses of the reagent blank and a series of standard solutions to determine the working standard range and the qualitative and quantitative detection limits for both atomic absorption analytical techniques. 4.1.2. The analytical method recovery results at all test levels were calculated from concentration response curves and statistically examined for outliers at the 99% confidence level. Possible outliers were determined using the treatment of outliers test, 5.10. In addition, the sample results of the two analytical techniques, at 0.5, 1.0 and 2.0 times their target concentrations, were tested for homogeneity of variances also at the 99% confidence level. Homogeneity of the coefficients of variation was determined using the Bartlett's test, 5.11. The overall analytical error, OAE, at the 95% confidence level was calculated using the equation, 5.12. OAE equals plus or minus, bias a plus, 1.96, CV1, pulled, 100%. 4.1.3. A derivation of the International Union of Pure and Applied Chemistry, IUPAC, detection limit equation, 5.13, was used to determine the qualitative and quantitative detection limits for both atomic absorption analytical techniques. CLD equals K, SD/M, equation 1, where CLD equals the smallest reliable detectable concentration an analytical instrument can determine at a given confidence level. K equals 3 for the qualitative detection limit at the 99.86% confidence level. SD equals standard deviation of the reagent blank, RBL, readings. M equals analytical sensitivity or slope as calculated by linear regression. 4.1.4. Collection efficiencies of metallic fume and dust atmospheres on 0.8 m mixed cellulose ester membrane filters are well documented and have been shown to be excellent. 5.11. Since elemental cadmium and the cadmium component of cadmium compounds are non-volatile, stability studies of cadmium spiked MCEF samples were not performed. 4.2. Equipment. 4.2.1. A Perkin-Elmer, P. Model 603 spectrophotometer equipped with a manual gas control system, a stainless steel nebulizer, a burner mixing chamber, a flow spoiler and a 10 cm. 1 slot burner head was used in the experimental validation of the flame AAS analytical technique. A PE cadmium hollow cathode lamp, operated at the manufacturer's recommended current setting for continuous operation, for milliamperes, was used as the source lamp. Instrument parameters are listed in attachment 1. 4.2.2. A PE model 5100 spectrophotometer, Xamon HGA 600 graphite furnace atomizer and a 60 HGA autosampler were used in the experimental validation of the AAS HGA analytical technique. The spectrophotometer was equipped with a PE Series 7700 professional computer and model PR310 printer. A PEAS System 2 cadmium electrodeless discharge lamp, operated at the manufacturer's recommended current setting for modulated operation, 170 mA, was used as the source lamp. Instrument parameters are listed in Attachment 2. 4.3. Reagents. 4.3.1. J.A.T. Baker Chemistry Company. Analyzed grade, concentrated nitric acid, 69.0 to 71.0%, and concentrated hydrochloric acid, 36.5 to 38.0%, were used to prepare the samples and standards. 4.3.2. Ammonium phosphate, monobasic, NH4H2PO4 and magnesium nitrate, Mg, NO3, 26H2O, both manufactured by the Mallinckrodt Chemistry Company, were used to prepare the matrix modifier for AAS-HGA analysis. 4.4. Standard preparation for flame AAS analysis. 4.4.1. Dilute stock solutions, prepared 0.01, 0.1, 1, 10 and 100 g/ml cadmium standard stock solutions by making appropriate serial dilutions of a commercially available 1000 g/ml cadmium standard stock solution, Rika Chemical Company, lot #A102, with the diluting solution, 4% HNO3, 0.4% HCl. 4.4.2. Analyzed standards, prepared cadmium standards in the range of 0.001 to 2.0 g/ml by pipetting 2 to 10 ml of the appropriate dilute cadmium stock solution into a 100 ml volumetric flask and diluting to volume with the diluting solution. See Section 3.7.2. 4.5. Standard preparation for AAS-HGA analysis. 4.5.1. Dilute stock solutions, prepared 1, 10, 100 and 1000 nanograms per milliliter cadmium standard stock solutions by making appropriate serial dilutions of a commercially available 1000 g/ml cadmium standard stock solution, J.T. Baker Chemical Company, Instra-analyzed, lot #D22642, with the diluting solution, 4% HNO3, 0.4% HCl. 4.5.2. Analyzed standards, prepared cadmium standards in the range of 0.1 to 40 nanograms per milliliter by pipetting 2 to 10 milliliters of the appropriate dilute cadmium stock solution into a 100 milliliters volumetric flask and diluting to volume with the diluting solution. See Section 3.8.2. 4.6.1. Analyzed the reagent blank solution and the entire series of cadmium standards in the range of 0.001 to 2.0 g/ml 3 to 6 times according to the instructions given in Section 3.10. The diluting solution, 4% HNO3, 0.4% HCl, was used as the reagent blank. The integration time on the P603 spectrophotometer was set to 3.0 seconds, and a fourfold expansion of the absorbance reading of the 2.0 g/ml cadmium standard was made prior to analysis. The 2.0 g/ml standard gave a net absorbance reading of 0.350 abs. Units prior to expansion in agreement with the manufacturer's specifications. 5.6. 4.6.2. The net absorbance readings of the reagent blank and the low concentration CD standards from 0.001 to 0.1 g/ml and the statistical analysis of the results are shown in Table I. The standard deviation, SD, of the 6 net absorbance readings of the reagent blank is 1.05 abs. Units. The slope, m, as calculated by a linear regression plot of the net absorbance readings, shown in Table 2, of the 0.02 to 1.0 g/ml cadmium standards versus their concentration is 772.7 abs. Units/g/ml. 4.6.3. F. These values for SD and the slope, m, are used in ECN. 1. SACT. 4.1.3. The qualitative and quantitative detection limits as determined by the IUPAC method are CLD equals 3, 1.05 abs. Units, /772.7 abs. Units/g/ml, CLD equals 10, 1.05 abs. Units, /772.7 abs. Units/g/ml. The qualitative and quantitative detection limits for the flame AAS analytical technique are 0.041 G and 0.14 G cadmium, respectively, for a 10 ml solution volume. These correspond, respectively, to 0.2 micrograms per cubic meter and 0.70 micrograms per cubic meter for a 200 L air volume. 4.6.4. The recommended CD standard working range for flame AAS analysis is 0.02 to 2.0 G/ml. The net absorbance readings of the reagent blank and the recommended working range standards and the statistical analysis of the results are shown in Table 2. The standard of lowest concentration in the working range, 0.02 G/ml, is slightly greater than the calculated quantitative detection limit, 0.014 G/ml. The standard of highest concentration in the working range, 2.0 G/ml, is at the upper end of the linear working range suggested by the manufacturer, 5.6. Although the standard net absorbance readings are not strictly linear at concentrations above 0.5 G/ml, the deviation from linearity is only about 10% at the upper end of the recommended standard working range. The deviation from linearity is probably caused by the fourfold expansion of the signal suggested in the method. As shown in Table 2, the precision of the standard net absorbance readings are excellent throughout the recommended working range. The relative standard deviations of the readings range from 0.009 to 0.064. 4.7. Detection limits and standard working range for AAS-HGA analysis. 4.7.1. Analyze the reagent blank solution and the entire series of cadmium standards in the range of 0.1 to 40 nanograms per milliliter according to the instructions given in section 3.11. The diluting solution, 4% HNO3, 0.4% HCl, was used as the reagent blank. A fresh aliquot of the reagent blank and of each standard was used for every analysis. The experimental characteristic mass value was 0.41 pg, calculated from the average peak area, ABS/SEC, reading of the 5 nanograms per milliliter standard, which is approximately midway in the linear portion of the working standard range. This agreed within 20% with the characteristic mass value, 0.35 pg, listed by the manufacturer of the instrument, 5.2. 4.7.2. The peak area, ABS/SEC, readings of the reagent blank and the low concentration CD standards from 0.1 to 2.0 nanograms per milliliter and statistical analysis of the results are shown in Table 3. 5 of the reagent blank peak area readings were 0 and the 6th reading was 1 and was an outlier. The near lack of a blank signal does not satisfy a strict interpretation of the IUPAC method for determining the detection limits. Therefore, the standard deviation of the 6 peak area readings of the 0.2 nanograms per milliliter cadmium standard, 0.75 ABS/SEC, was used to calculate the detection limits by the IUPAC method. The slope, m, as calculated by a linear regression plot of the peak area, ABS/SEC, readings, shown in Table 4, of the 0.2 to 10 nanograms per milliliter cadmium standards versus their concentration is 51.5 ABS/SEC/ing/ml. 4.7.3, if 0.75 ABS/SEC, SD, and 51.5 ABS/SEC/ing/ml, m, are used in ECN. 1. SACT. 4.1.3, the qualitative and quantitative detection limits as determined by the IUPAC method are CLD equals 3, 0.75 ABS/SEC, / 51.5 ABS/SEC/ing/ml, CLD equals 10, 0.75 ABS/SEC, / 51.5 ABS/SEC/ing/ml equals 0.15 nanograms per milliliter for the quantitative detection limit. The qualitative and quantitative detection limits for the AAS-HGA analytical technique are 0.44 ing and 1.5 ing cadmium, respectively, for a 10 milliliter solution volume. These correspond, respectively, to 0.007 micrograms per cubic meter and 0.025 micrograms per cubic meter for a 60 L air volume. 4.7.4. The peak area, ABS/SEC, readings of the CD standards from 0.2 to 40 nanograms per milliliter and the statistical analysis of the results are given in Table 4. The recommended standard working range for AAS-HGA analysis is 0.2 to 20 nanograms per milliliter. The standard of lowest concentration in the recommended working range is slightly greater than the calculated quantitative detection limit, 0.15 nanograms per milliliter. The deviation from linearity of the peak area readings of the 20 nanograms per milliliter standard, the highest concentration standard in the recommended working range, is approximately 10%. The deviations from linearity of the peak area readings of the 30 and 40 nanograms per milliliter standards are significantly greater than 10%. As shown in Table 4, the precision of the peak area readings are satisfactory throughout the recommended working range. The relative standard deviations of the readings range from 0.025 to 0.083. 4.8. Analytical method recovery for flame AAS analysis. 4.8.1. For sets of spiked MCF samples were prepared by injecting 20 L of 10, 50, 100 and 200 G/ml dilute cadmium stock solutions on 37 mm diameter filters. Part No. AAWP 03700, Millipore Corporation, Bedford, Massachusetts, with a calibrated micropipette. The dilute stock solutions were prepared by making appropriate serial dilutions of a commercially available 1000 G/ml cadmium standard stock solution, Rika Chemical Company, lot #A102, with the diluting solution, 4% HNO3, 0.4% HCl. Each set contains 6 samples and a sample blank. The amount of cadmium in the prepared sets were equivalent to 0.1, 0.5, 1.0, and 2.0 times the TWAPL target concentration of 5 micrograms per cubic meter for a 400 L air volume. 4.8.2. The air-dried spiked filters were digested and analyzed for their cadmium content by flame atomic absorption spectroscopy, AS, following the procedure described in Section 3. The 0.02 to 2.0 G/ml cadmium standards, the suggested working range, were used in the analysis of the spiked filters. 4.8.3. The results of the analysis are given in Table V. One result at 0.5 times the TWAPL target concentration was an outlier and was excluded from statistical analysis. Experimental justification for rejecting it is that the outlier value was probably due to a spiking error. The coefficients of variation for the 3 test levels at 0.5 to 2.0 times the TWAPL target concentration passed the Bartlett's test and were pooled. 4.8.4. The average recovery of the 6 spiked filter samples at 0.1 times the TWAPL target concentration was 118.2% with a coefficient of variation, CV1, of 0.128. The average recovery of the spiked filter samples in the range of 0.5 to 2.0 times the TWA target concentration was 104% with a pooled coefficient of variation, CV1, of 0.010. Consequently, the analytical bias found in these spike sample results over the tested concentration range was plus 4% and the OA was plus or minus 6.0%. 4.9. Analytical method recovery for AAS-HGA analysis. 4.9.1. 3 sets of spiked MCF samples were prepared by injecting 15 L of 5, 10, and 20 G/ml dilute cadmium stock solutions on 37 mm diameter filters. Part No. AAWP 03700, Millipore Corporation, Bedford, Massachusetts, with a calibrated micropipette. The dilute stock solutions were prepared by making appropriate serial dilutions of a commercially available certified 1000 G/ml cadmium standard stock solution, Fisher Chemical Company, lot #913438-24, with the diluting solution, 4% HNO3, 0.4% HCl. Each set contains 6 samples and a sample blank. The amount of cadmium in the prepared sets were equivalent to 0.5, 1 and 2 times the action level TWA target concentration of 2.5 micrograms per cubic meter for a 60 L air volume. 4.9.2. The air-dried spiked filters were digested and analyzed for their cadmium content by flameless atomic absorption spectroscopy using a heated graphite furnace atomizer following the procedure described in Section 3. A 5-fold dilution of the spiked filter samples at 2 times the action level TWA was made prior to their analysis. The 0.05 to 20 nanograms per milliliter cadmium standards were used in the analysis of the spiked filters. 4.9.3. The results of the analysis are given in Table 6. There were no outliers. The coefficients of variation for the 3 test levels at 0.5 to 2.0 times the action level TWAPL passed the Bartlett's test and were pooled. The average recovery of the spiked filter samples was 94.2% with a pooled coefficient of variation, CV1, of 0.043. Consequently, the analytical bias was minus 5.8% and the OAE was plus or minus 14.2%. 4.10 Conclusions. The experiments performed in this evaluation show the two atomic absorption analytical techniques included in this method to be precise and accurate and have sufficient sensitivity to measure airborne cadmium over a broad range of exposure levels and sampling periods. 5. References. 5.1. Slavin, W. Graphite Furnace AS, a sourcebook, Perkin-Elmer Corporation, Spectroscopy DIV, Ridgefield, Connecticut, 1984, p. 18 in pages 83 to 90. 5.2. Grosser, Zig ed. Techniques in Graphite Furnace Atomic Absorption Spectrophotometry, Perkin-Elmer Corporation, Spectroscopy DIV, Ridgefield, Connecticut, 1985. 5.3. Occupational Safety and Health Administration Salt Lake Technical Center, Metal and Metalloid Particulate in Workplace Atmospheres, Atomic Absorption, OSHA Method No. ID 121. In OSHA Analytical Methods Manual, 2nd edition. Cincinnati, Ohio, American Conference of Governmental Industrial Hygienists, 1991. 5.4. Occupational Safety and Health Administration Salt Lake Technical Center, Metal and Metalloid Particulate in Workplace Atmospheres, ICP, OSHA Method No. ID 125G. In OSHA Analytical Methods Manual, 2nd edition. Cincinnati, Ohio, American Conference of Governmental Industrial Hygienists, 1991. 5.5. Winhalls, M. ed., The Merck Index, 10th edition, Merck & Company, Rahway, New Jersey, 1983. 5.6. Analytical Methods for Atomic Absorption Spectrophotometry, The Perkin-Elmer Corporation, Norwalk, Connecticut, 1982. 5.7. Slavin, W. D. C. Manning, G. Karnrick, N.E. Praskowska, Properties of the Cadmium Determination with the Platform Furnace and Zeeman Background Correction. Spectrochem. Acta 38B 1157-1170, 1983. 5.8. Occupational Safety and Health Administration Salt Lake Technical Center, Standard Operating Procedure for Atomic Absorption. Salt Lake City, Utah, OSHA SLTC, in progress. 5.9. Occupational Safety and Health Administration Salt Lake Technical Center, AASHGA Standard Operating Procedure. Salt Lake City, Utah, OSHA SLTC, in progress. 5.10. Mandel, J. Accuracy and Precision, Evaluation and Interpretation of Analytical Results, The Treatment of Outliers. In Treatise on Analytical Chemistry, 2nd edition, Volume 1, edited by I. M. Kalthoff and P. J. Alving. New York, John Wiley & Sons, 1978. Pages 282 to 285. 5.11. National Institute for Occupational Safety and Health, Documentation of the NIOSH Validation Tests by D. Taylor, R. Cupel, N.J. Bryant, DHEW/NIOSH Pub. No. 77 to 185, Cincinnati, Ohio, National Institute for Occupational Safety and Health, 1977. 5.12. Occupational Safety and Health Administration Analytical Laboratory, Precision and Accuracy Data Protocol for Laboratory Validations. In OSHA Analytical Methods Manual, 1st edition. Cincinnati, Ohio, American Conference of Governmental Industrial Hygienists, Pub. No. ISBN 0-936712-66X, 1985. 5.13. Long, G. L. and J. D. Weinfordner, Limit of Detection, a close. Our look at the IUPAC definition. Anal. Chemistry. 55:712A724A, 1983. 5.14. American Conference of Governmental Industrial Hygienists, Documentation of Threshold Limit Values and Biological Exposure Indices. 5th edition. Cincinnati, Ohio, American Conference of Governmental Industrial Hygienists, 1986. See OSHA Standard for Table I CD Detection Limit Study. See OSHA Standard for Table 2 CD Standard Working Range Study. See OSHA Standard for Table 3 CD Detection Limit Study. See OSHA Standard for Table 4 CD Standard Working Range Study. See OSHA standard for Table 6 Analytical Method Recovery.